I have the pleasure of introducing our next speaker. He is an internationally renowned fisheries ecologist and environmental physiologist who has over 161 publications in the primary literature, reports, and in book contributions. He is also a passionate angler and hunter. Dr. John Casselman is an adjunct professor in the biology department at Queen's University and former senior scientist who supervised fisheries research on Lake Ontario for the Ministry of Natural Resources and Forestry. He has received several awards for his work, including the American Fisheries Society Award of Excellence, the Great Lakes Fishery Commission Distinguished Scientific Contributions Award, and last month, Dr. Casselman was voted into the Canadian Angler Hall of Fame. For many years, the OFAH has not only benefited from Dr. Casselman's research, but also directly from his knowledge and passion as a member of our OFAH Fisheries Advisory Committee. I first met Dr. Casselman more than a decade ago when I was an undergraduate student. As an aspiring biologist, I could not help but be inspired by his infectious passion for fisheries science. I was struck by Dr. Casselman's dedication to fisheries management. His research had a purpose and always intended to answer important questions directly applicable to fisheries management. I can say with absolute certainty that Ontario's fisheries are better for it. From the Great Lakes Basin to Ethiopia, from the Canadian Arctic to Tibet, he has conducted research on climate change, fish, and fisheries around the world. Please join me in welcoming Dr. John Casselman to speak on the relationships between climate change and fisheries.
Well, thanks, Matt. They were very kind words. I certainly appreciate the opportunity to be here and to talk about climate change, fisheries, and fishing, and shifting baselines. Now, my presentation is heavily into graphics, as it usually is, and I'm really going to have a problem here because I use a laser pointer a lot. So I'm not sure which particular illustration I should point at. They seem a long ways off. But anyway, will try to see what I can do about this. So I want to talk about climate change and the fact that it's already affecting aquatic fish resources, fish and fisheries. And environmental conditions are changing and becoming more variable. They're creating different conditions and shifting baselines. I think that's really an important point, that the baselines are shifting. Fish and fisheries can be very sensitive to these environmental influences. And often these changes are not very obvious. They're obscure and they're often unexpected. The question is, do we appreciate these changes and are we adapting to them? Will climate change create new recreational fishing opportunities? And I think that's an important point to consider. So the objectives of the presentation is I want to examine changing environmental conditions and baselines in Ontario and Ontario water bodies and consider trends and variability. I want to examine the response of sport fish and fish communities to these using long-term data sets and try to determine if we can predict what might go on and how we might adapt to these changes. I want to consider how we might manage and adapt to help sustain fish resources and human endeavors in a changing and more variable climate. I think that's really important, that we need to make sure that we can sustain human endeavors. So change is underway. I guess the question is, are we detecting it? And truly, are we managing for it? To me, this is given your keynote speaker, this is a slide that I could spend a lot of time on, because I think it's really important. I think that to fish is to have faith. And if you think about that, I think resource users, fishers and hunters, have faith. In fact, they're optimists. And I think that's a very important point too. Fishers are ever the optimists, and I fish. And you can't beat being there. In fact, if you've been there long enough, like I have, to some extent you see some of these changes. And these changes are more obvious. Observant anglers know that climate, especially temperature, affects fish and fishing. Temperature is a major controlling factor. We know that. It directs activity, and that's something that we haven't thought a lot about as anglers. And maybe we do. Successful anglers do, I think. Also, it affects feeding, growth, and recruitment or production. And the response really depends upon the thermal requirements of the species. So I'm going to talk a lot about that today. We need to know something about the temperature requirements of the fish. But first of all, how are temperatures changing? And I think you might be interested in this. What I've done is I've looked at a number of long-term data sets, and I've looked at temperature actually from the Bay of Quinte at the Belleville pumping station. And it's very good temperature data because it's a backwater area. It's not affected by the seshing and the wind action of Lake Ontario, and it is long-term data. And I'd like to look at this in terms of how temperature has changed over the past, 75 years. So let's look at global warming and changing thermal conditions in these shifting thermal baselines. So here is essentially the open water period. It's more or less the growth period of many fish species. And it's April to September, and it's the Bay of Quinte water temperatures. And on the top graph, it's actually the mean value for that period of time, from April to September. And you can see that there is definitely an increase, and that increase over that period of time, which is 75 years, is 1.5 degrees Celsius. So the water temperatures in the Bay of Quinte have increased 1.5 degrees Celsius. And you may say, well, that's not very much, John, so how could that be significant? I suggest you stay tuned and see what that has done to fish communities and what can do to fish communities. The bottom graph it's not fancy statistics, actually. What we do on the bottom graph is we take the mean value and we actually look at each individual year and we calculate what the difference is between that year and the mean value. And if it's positive, we add it. If it's negative, we subtract it. So it actually is an accumulation of the change over time. And all you need to do is look at the years that are highlighted, and it tells you when change over that period of time really started to happen. And what it suggests is that in the 70s, the water temperatures in the Bay of Quinte started to increase rather dramatically. In fact, there was a thermal regime shift in the northern hemisphere, best seen in the Pacific, in the northern Pacific, where the temperatures actually started to change dramatically in mid-70s, actually 76, 77, 77, 78. So you can see there's been a few setbacks here which are quite interesting, and I'll talk about those in a few minutes. The thing that's interesting is you say, well, that's not much in the change of temperature. So let's look at what it does to evaporation. For every 1 degree temperature increase, there's a 6% increase in the evaporation rate. So over that period of time, we have seen an increase in the evaporation rate of 10%. We've noticed that. We've noticed there's less water around. And the water distribution is changing rather dramatically. So it's really that we're actually seeing droughting in relation to that period of time. A 10% increase in the evaporation rate. Now let's look at the very high temperatures. What's happened to the highest temperatures? Let's look at the temperatures above 20 degrees Celsius. And this is water temperature in the Bay of Quinte. And what we see is a major increase in the number of days where the water temperature is above 20 degrees Celsius. The average is about 90, and that's an increase of about 20 days. So the summers are actually getting warmer. And you can see, according to the graphics, that this actually started in fact, in the 80s, in the most dramatic way. Ice cover. Well, ice cover is really indicative. And if you look at ice cover in the Bay of Quinte, you can see that the QSUM tells us that the ice cover started to diminish in the Bay of Quinte, actually in the 80s, rather dramatically in the 80s. And you can see some years where the ice cover in the number of days was very much shorter. Notice the last couple of winters. Very, very major increase in the ice cover in the Bay of Quinte. And we've noticed that. We've noticed the last couple of winters, the last few years have been quite different, and we should look at that in terms of what it might indicate. But you can see that the trend is, in fact, a significant decrease in the ice cover in the Bay of Quinte. The temperature data that I like to look at a lot is the summer temperatures, what I call the midsummer temperatures. It's the July-August temperatures in the Bay of Quinte. And if you look at them, these are the midsummer temperatures. They've increased as you would expect, and you can see that they started really in the 60s to increase. They're the ones that drive a lot of fish production, or they're indicative of fish production. So I'm going to look at those a lot, and they're important to us, and I want to relate those to how what we might see in global changes. And I'm going to do that by actually going to the tropical Pacific. I'm going to go to the tropical Pacific, and I'm going to look at the El Nino and La Nina. Now, the El Nino events are the warm events in the tropical Pacific, and the La Nina events are the cold events in the tropical Pacific. And you can see for this period of time from 1950 to the present, you can see that in the first few decades, 50, 60, and in the 70s, you can see many more La Nina events, very cold period. Then we went through a period of a couple of decades of very, very warm period. And now we see kind of an indifferent period. We see some El Niños, some La Niñas, and in fact the La Niña of 2009 was rather extreme, and in fact we saw that actually in the Great Lakes Basin. The interesting thing is that if you look at the temperature in the tropical Pacific, those are the temperatures, the extreme temperatures that we see in water temperatures in the Bay of Quinte 2 to 8 months later. And we see 75% of the La Nina events directly expressed in the Bay of Quinte 2 to 8 months later, and 75% of the El Nino events. So you can go to the tropical Pacific and you can get some insights about what water temperatures you're going to see in the next 6 to 8 months. Now the thing that's interesting is there seems to be a disconnect in recent years. And I want to talk about that because I think that's kind of interesting. The trends are there, but there's some differences in recent years. And I want to address to some extent why these differences might be occurring a little later in my talk. Sorry about the busyness of the graph, but this is in fact the July-August water temperatures. And I want to use them, and I got arrows beside some of these. These arrows are kind of important, but this is what it amounts to. What it amounts to is that if it's a large arrow up, it's an El Nino event that's expressed in the Bay of Quinte that was also prominent in the tropical Pacific. And you can see that in recent years there are more El Nino events expressed. Very recently, though, there is some evidence here of there's warming temperatures in the Bay of Quinte that are not directly related to El Nino events. So something's going on here that we're starting now to see maybe global changes that are really being expressed independent of what's going on in the tropical Pacific. In other words, it's in the northern hemisphere. Now, if we look at the La Nina events, you can see that most of the La Nina events, in fact, were early on in this period, in the 40s, 50s, and to some extent the 60s. And so you can see that there is a trend in that data. That trend is significant, obviously. I've talked about that a little bit earlier. There's one quite interesting. There's, as I said, 75% of them are expressed. There's some years where they're not expressed. And that's actually in recent years. There are some La Nina events in the tropical Pacific in recent years, minor ones that are not being expressed in the Bay of Quinte. There's one very interesting event here that is an El Nino event in the tropical Pacific, but it's not expressed in the Bay of Quinte, and it's 1992. And in 1992, there was in fact a volcanic eruption. 91 actually, Mount Pinatubo, and that volcanic ash went around the atmosphere for in fact 3 years, and it dropped the temperature in the northern hemisphere rather dramatically, overrode an El Nino event. There are some other actually volcanic eruptions in that data I don't have time to go into now, which are quite interesting. So there's a global phenomenon going on here. So what I want to look at is water and air temperature. You notice I'm dwelling on water temperature. Water temperature is far more indicative of thermal change than air temperature. Air temperature is extremely variable. And the reason why water temperature is more indicative is it warms up in relation to ambient temperature, but it also receives the radiation that's coming in from the sun, which is a thermal radiation which is actually being trapped as radiant energy in the earth. Sorry about the graph, okay? It's more or less for my purposes. What I want to show here is that from May to, in fact, November, we are, in fact, seeing water temperatures in the Bay of Quinte that are warmer than air temperatures. And on the average, they're 3 degrees warmer than air temperatures. So think about that. Although we think about air temperature, this is what affects the fish. So the fish are affected by this increasing temperature and the fact that radiation is, in fact, coming in. So water temperature is, I think, far more indicative of the global changes we're seeing than, in fact, is air temperature. And as I always tell my students, we don't find correlations often between fish community effects and air temperature, but we look at water temperature, we find it. So water temperature is much more indicative, and the water indicates that thermal radiation is increasing substantially. In fact, that's the difference between those is 21%. It's 21% warmer in the water than it is in the air on the average. So let's look now at water. Well, I worked with some colleagues in Mississippi Valley Conservation Authority, and they've done a lot of work on modeling the Mississippi River. And the Mississippi River, of course, flows into the Ottawa, and there's some really interesting data here. I'll talk about the Mississippi a little more later, but I think this is important to consider. If you look at what all of the modeling they've done about discharge in the Mississippi River, there's one thing that stands out, one prominent thing, and that is that the fall and winter discharges in the Mississippi River is increasing substantially. And this is related to the fact that over this period of time, because of this global warming, we've lost actually the snowpack and the ice pack, so we have direct runoff in the fall and winter. Now, there's been some changes recently, I know that. And you can see that this actually goes way back in terms of the Mississippi, back to the 60s, when that really started, and in fact, more prominently in the 70s. Well, what they did is they did some modeling, and they said, well, what's going to happen here? So what they did is they took data that was actually from the 1900s to 1970s, and they looked at the discharge in the Mississippi, and then they looked at the Mississippi from the 1970s to the 2000s, and they said, well, let's take that now and model it for the next 100 years. So they modeled it for the next 100 years, and they come up with something that was quite interesting. These, in fact, are about 30-year intervals. In fact, I guess the first interval is, in fact, the one that you could think of related to 2038. So what it shows is that, in fact, the spring runoff will diminish, and, in fact, it'll become earlier. In fact, what they showed, besides this 70% increase in the fall and winter runoff, they showed that the spring flows would be 33% lower in the spring, so there'd be less spring runoff, and the peak runoff would be 6 to 7 weeks earlier, just dramatically. Dramatic. And the summer flows would be lower by 44%, and they would last 28% longer. So there's some dramatic changes there in how that small river will respond in the next 100 years, given the modeling that they were doing. So now I need to look now at fish communities and fisheries and how they might respond. And the most important part of this is the thermal requirements. I need to know what are the thermal requirements of the species. I think you can see this table because I think it's a very important one. The top group are the warm water fish. The middle group are the cool water fish. Bottom group are the cold water fish. The warm water fish, they do best at temperatures in the high 20s, actually. These are preferred or optimum temperatures. And the best example there, I'll talk about a little bit later, is smallmouth bass. And these fish, in fact, are summer spawners. They spawn in the summer. The cool water fish, they do best in the low 20s, and pike and walleye are there. Walleye is an important species, of course, about 22.2. I don't know if you noticed, but the Bay of Quinte is running now about 23, so it's starting to go above the optimum for walleye, which is kind of interesting. And these fish are spring spawners. And then the cold water fish, optimum maybe 10 to 15 degrees C. Best example there is lake trout, and they're very different. They drop their eggs in the late fall. The eggs then develop in relation to temperature. Then the development slows down. They go through dormancy in the winter, and then they hatch in the spring. So the winter, the fall, the cold water fish are very different. They're fall spawners. So let's look at recruitment now. What's going to happen? What's going to happen in relation to temperature? How many young fish are going to be produced in relation to temperature? Well, this comes from data from the Bay of Quinte, and we're very fortunate we have these long-term data sets and from Lake Ontario. And on the left are the year class strengths in different years, and a number of small bass, young bass produced each year. And we put that in relation to temperature, and you can see we have a linear relationship. In other words, at warmer temperatures, these are midsummer temperatures, we have greater recruitment of bass. We have more young bass produced. The thing that's interesting about this is that bass recruitment on the y-axis is not linear. It's not going in units. but it's going in tens. In other words, it's a log value. If in the bottom of the graph, I'm trying to show you what might happen, what does happen. In fact, if the water temperature increases 1 degree Celsius for bass, we move up the average scale here 1 degree, we see an increase in recruitment of 2.5-fold. That's not percent, that's fold. 2.5 times as many young bass produced. 2 degrees, we see, in fact, a 6-fold increase, and with 3 degrees, we see a 14-fold increase in young bass. Now, the interesting thing is that moves up and down on that relationship. In the Bay of Quinte and eastern Lake Ontario, the water temperatures over that period of time changed 2.8 degrees Celsius, plus or minus 2.8 degrees Celsius up or down. So it's gone up and down that scale, that particular amount. So that means that these managers have had to manage bass populations that have fluctuated over that period of time in terms of recruitment by 2 times about 15-fold, which is 30-fold changes, with very dramatic changes. Now, the thing that's interesting is if you look at the Pinatubo event, you can see the Pinatubo event meant very few bass were produced. In fact, all the major year classes of bass came from El Nino events, and all the weak year classes came from La Niña events, and the Pinatubo event is right on the line. Let's look at northern pike, and it's interesting. Northern pike correlation is exactly the same. It's actually with July-August water temperatures. Now, that's a temperature relationship. And if you look at pike now, you can see we got data, long-term data from the Bay of Quinte and eastern Lake Ontario. You can see a curvilinear relationship in relation to it, and it's also a log value. So what that suggests is if you increase the water temperature 1 degree Celsius, as we've done here, we get a decrease of almost 2.5 times as many young pike produced. We increase it 2 degrees, we get almost 18 times as many, as few young pike produced. So you can see that if you increase the water temperatures for pike, you can see as the temperature increases, the recruitment's going to decline rather dramatically, many-fold. Lake trout, well, unfortunately, we lost lake trout from Lake Ontario, so we don't have the same kind of data, but we did a lot of incubation studies where we put the eggs in rock rubble, fertilized eggs in rock rubble, and we examined whether the eggs developed the next spring when they would have emerged. And we also did experiments in the laboratory, and what we showed was this relationship on the right, which is the fry survival at emergence the next spring, the percent survival, and in relation to the spawning temperature. And what it basically shows is at high spawning temperatures, we have virtually no survival whatsoever. And at low spawning temperatures, we have, in fact, a fairly high survival of about 25% at low temperatures. So if we increase the water temperature at spawning time by 1 degree, we get about a 1.5-fold fewer small young lake trout. And if we increase it 2 degrees, we get about a 2.4-fold decrease in young lake trout. If we increase it 3 degrees, we get a major decrease in the recruitment of young lake trout, about 20%, 20-fold, about 20-fold decrease. That's really dramatic. Now, what's going on here? What's going on here is that at high temperatures, when the eggs are deposited, they start to develop rapidly, and they actually premature hatch. The next slide is, I'm sorry about it, it's rather complicated, but it's very straightforward, really, if you think about it. These are the water temperatures in Lake Ontario over the time that lake trout would drop their eggs, and these are, in fact, the heat units that the eggs would absorb, and this is the percent hatch on the right. And it indicates that lake trout that drop their eggs at about 12 degrees Celsius actually accumulate enough heat units to completely hatch in December. And they then absorb their yolk sac. It takes 6 weeks for them to absorb their yolk sac, and they die. So that premature hatch is really important if the eggs are dropped at high temperature. In fact, in Lake Ontario, we can actually double the recruitment in the spring if the eggs are dropped 9 days later. That's 2 degrees Celsius, just 9 days later. Well, you might say, well, why don't lake trout just follow temperature when they drop their eggs? Lake trout and cold water species don't. They don't follow temperature at spawning. They follow photoperiod. So almost in every lake in Ontario, we find that lake trout will, in fact, drop their eggs at about the same time every year. And this is related to the basin and photoperiod. So that's interesting. So if they drop their eggs and the year is a warm year, you're going to have premature hatch. If it's a cold year, you're going to have recruitment. So what that's going to tell you is these cold water species, and in fact lake herring and whitefish are exactly the same. In cold falls and cold winters, you're going to in fact see recruitment of cold water species. When I arrived in Lake Ontario, I interviewed some of the oldest commercial fishermen I could find about what they thought produced lake trout and whitefish. And they said, John, the coldest falls and the coldest winters. That's my fancy science, showing exactly what observant fishers, anglers, and know. Which is really quite interesting, actually. I think that when you take that into consideration, then you worry a bit about the fact as well, if the falls and winters are in fact getting warmer, is this affecting the recruitment of whitefish and lake trout? I would suggest to you that I applaud you, in fact, for having the fisheries opened up in Simcoe, because the lake herring and Lake Simcoe actually have a climate signal in their recruitment. And the fact that now they've appeared again because of some cold falls and cold winters, we should use that resource. Well, this is the December water temperatures in the Bay of Quinte. And as you can see, back in the 70s, in fact, we had some very, very cold years in the Bay of Quinte. In fact, this mean value is, in fact, very close to what would be ice cover. In the December temperatures below that, the Bay of Quinte would be frozen in December. Above that, the Bay of Quinte would be open. And you can see that the December water temperatures really started to increase rather dramatically in the Bay of Quinte in the mid-90s in December. And you can see the last few years here a fairly major drop, which is quite interesting. So you can see a playoff here, can't you, between warm years giving us bass and cold years giving us the cold water species. Really quite important. Well, what I tried to do here was I thought, well, if I know something about when lake trout spawn, can I take those spawning temperatures and look at what we might see over time in terms of what we could expect for lake trout recruitment. And what I did on the top graph is that's the mean water temperature for the last week in October and the first 2 weeks in November. And that's essentially kind of a universal spawning time for lake trout. I know it doesn't cover all water bodies, but it's kind of universal. And then I used that relationship I had on the right side of that graph to estimate what would be the predicted emergence. And then I look at Q-sum. Well, the thing that's interesting is we can see the recruitment in the early 80s started to decrease rather dramatically in lake trout, according to these temperatures. And in fact, that decline in water temperature that increase in water temperature is in fact significant over that period of time. And you can see some years, where the water temperatures actually were low enough that we've probably had pretty significant recruitment of lake trout. But it's sporadic. Lake trout are very long-lived fish. And I say they invest in longevity, live long enough to spawn in cold regimes. So are we seeing declining lake trout? Well, there's many factors that could affect lake trout recruitment. I know that, but I want to show you that if we look at Quebec lakes, 99 Quebec lakes and 58 Ontario lakes, and you look at year class strength of lake trout, you can see a fairly major decline over that period of time, from the 1950s to the 2000s. The Q-sum says that it was probably a little bit earlier in Quebec than it was in Ontario, but it's rather major. And the thing that's interesting is that recruitment is negatively correlated with July-August water temperatures. So July-August water temperatures have increased, and the recruitment of lake trout across those water bodies, particularly in Quebec, shows a negative relationship. Well, the thing that's interesting is that if you want to see probably the species best adapted to spawning in high temperature, you should go to the southern part of the range. For example, if you go to Oneida Lake, the Oneida lake trout actually spawn very late, about a month later than most of our Ontario stocks. And they're now selected to be better adapted to, in fact, higher water temperatures in the basin and at the latitude. The thing that's interesting is we're starting to see in Ontario lake trout actually spawning below the thermocline. Now, don't hold your breath, because that's not going to give you fish production. What it is going to maintain the species, and that's about all it's going to do, which is really kind of interesting when you think about it. But they are actually in Ontario lakes. There are areas where lake trout are actually now spawning in September below the thermocline. Well, midsummer depth distribution and behavior. We'll think about this for a few minutes now. We know that, and this is a kind of an interesting graph, a really informative graph, I think, because what it is, it's a hypothetical basin of a lake. It shows you the size of lake trout and where they're found in the depths in the lake. And what it says is that the smallest lake trout are found in the deepest part of the lake, and they live there for up to about 4 years. Now that's kind of interesting, because that's really important. So they're down there, and they live there about 4 years, and as long as the environmental conditions are good, there's lots of oxygen. They're separated from the large lake trout. The large lake trout are shallower, and you can see the biggest lake trout are in fact a bit deeper. And we know from looking at stomach contents of some lake trout and flesh color that these big lake are in fact cannibalistic. They're preying down in the young juvenile lake trout. The thing now what happens is, if you look at this, and if you lower the thermocline, that starts a squeeze from the top. So it pushes the big lake trout down closer to the juvenile lake trout. I should emphasize the fact that if you look at Ontario lakes on the average, in Ontario lakes, on the average, only 3% of the volume of the lake is juvenile habitat. It's the factor that's limiting our lake trout production. So the thing is, if we take and push the thermocline down, you can see the large lake trout are going down. And then what happens is, in climate change, often we see increased phytoplankton production. We see more dead plankton raining down into the deep waters of the lake. And we know what can happen with cottage development there. We can lose that hypolimnetic, that deep oxygen in the lower. So we have now an oxygen depletion in the bottom, which actually pushes the juveniles up. It pushes the juveniles up, and if they're in the presence of the large lake trout, they're goners. That's all there is to it. They're prey. So that's a really important explanation, I think, of why we need to protect the bottom of the oxygen levels in the lake. And that squeeze is in one that in fact can go on. I want to be very clear about this. There is some debate about the depth of the thermocline. And I think that's interesting. I don't have time to go into that, but I think that's important. It may be that the thermocline might set up shallower because it sets up earlier. I don't know. But the evidence is that there is ample evidence that it's going to push the thermocline down. So this is a summary slide, okay? And the summary slide actually shows you what the fold change would be with 1 degree, 2 degrees, 3 degrees with the warm water, cool water, and cold water fish. Okay, let's try something that's kind of hypothetical here. Let's take a fish community that has 33%. A third of its recruitment comes from warm water, a third from cool water, and a third from cold water. And let's increase the water temperature 1 degree Celsius, just 1 degree. If we increase it 1 degree Celsius, then actually 69% of the recruitment comes from the warm water fish. And there's reduced recruitment, substantially reduced recruitment, in the cool and the cold water fish. In fact, now almost a twofold increase in the recruitment of warm water fish. So that tells you the warm water fish recruitment is going to increase substantially. Let's increase it now to 2 degrees, just 2 degrees. And if we do, 93% of the recruitment now switches to the warm water fish. And you can see cool water fish suffer rather significantly, and that's kind of interesting. I won't go into that right now, but that's rather interesting. And you can see a major decrease in cold water fish. So you can see those trends. Those trends are obvious. And I think avid, observant anglers know these changes are underway, and they're taking advantage of them. We did a study, in fact, on the Mississippi River system, and anglers on the Mississippi River system were starting to target these warm water fish rather substantially. And my attitude is they should be targeted. In fact, bass fishing in Ontario has never been better. Sizes are astronomical. I mean, I guided on the St. Lawrence. We would have thought we'd died and gone to heaven to catch some of the bass that we see today. And the catches are at record high levels. So this is going on. And anglers know this. Anglers tell me this. Observant anglers tell me this. Now the question is, does our science say this? Well, our science sure does, because if you look at the Bay of Quinte, and we have indices of abundance of a number of species in the Bay of Quinte, because we look at all species in these research studies and these assessment studies that the Glenora Fishery Station does. If you look at actually 8 sunfish species in the Bay of Quinte, you can see they are pretty level for a number of years, but lo and behold, in the late 90s, their numbers started to increase rather dramatically. Now, the important thing about these 8 species, there's not just smallmouth bass, there's rock bass, pumpkin seeds, bluegills. And the thing that is important is that overpopulation can result, and it can result in stunting if they're not fished and if they're not really thinned by exploitation. So they need to be thinned, they need to be fished, they need to be harvested to make sure that we don't have stunting of these warm water fish. The thing that was interesting in the Bay of Quinte is that, as I said, there's all kinds of very good data in those ministry files. What they showed was that the minnow species actually started to increase earlier. They started to increase in the early 90s. And of course, you know what happened to them. They were just prey to all of these panfish that actually started to explode in about 3 or 4 years later. So their abundance hasn't really been maintained in any great way. I'd like to bring those data sets up to date, see what's happened, because I think they're very, very, very informative. So invasive species and climate change, well, there's going to be shifting here. I want to talk about that because I want you to think about that a little bit, because there are shifts going on here. And you've probably seen some of these shifts. I want to talk about prey fish abundance, growth, and survival, and I want to go after the rock bass. Rock bass are a problem. They're a major problem, and they've invaded across Ontario. And they clean up the inshore fish community. They're the cats of the water. They just clean up the inshore fish community. And actually, very few small rock bass can actually devastate the small fish community inshore. So this is the long-term recruitment of rock bass in eastern Lake Ontario and the Bay of Quinte. And there's the relationship, and there it's just exactly similar to what we saw in smallmouth bass. It's a log relationship again, so let's look at the bottom part table, and if you look at the bottom, you can see these numbers. Hope you can. If you increase the water temperature 1 degree, you get 2-fold increase in rock bass. 2 degrees, you get almost a 4-fold increase in rock bass. 3 degrees, 8-fold increase in rock bass. And those are the species that's the life stage that actually disperses. It moves through river systems and it ends up in bait buckets. And that's part of the problem. It's these small rock bass that we need to worry about, and their numbers are exploding. Well, look at lake trout lakes. We looked at lake trout lakes through central Ontario, and we were electrofishing, so we looked at fish biomass. I was interested in what prey fish were there for lake trout. And if you look at prey fish for lake trout, many of these were small fish, small minnows. Some of them were in fact invasive themselves. And we looked at them, and then we looked at rock bass in these lakes, in the inshore fish community. And you can see where we had no rock bass, we had good lake trout prey abundance. Where we had rock bass, we had very poor lake trout prey abundance. And then we actually lived the story in a couple of lakes where we saw rock bass invade, and we saw the inshore fish community decline dramatically. Well, how important are these prey fish? Prey fish are really important in terms of growth and production of lake trout and fecundity of lake trout. In fact, work that Dave Brown did in those lakes showed rather dramatically that, in fact, if you look at the relationship across this scale where in fact rock bass invaded in these lakes, the lake trout now became slower growing. They became 30% smaller, 25% lighter. Now they were plankton feeders most of the time. And lake trout need minnows, in fact, to condition themselves for after spawning, actually. And in fact, the most important thing, there was a 40% decrease in fecundity. Now that was really important, because not only were the lake trout smaller, but they were less fecund. So you can see that jeopardizes lake trout production in those lakes. So the invasion of rock bass in lakes is not just lake trout. You can see their imprint on walleye. You can see their imprint on smallmouth bass. And smallmouth bass are just about as bad, but they're not quite as bad. And you can see their imprint on other important recreational large-bodied species. Well, one species that's invading rather dramatically, and I know you know this, in fact, that black crappie. Black crappie, in fact, are walleye predators. And their abundance is increasing rather dramatically. And it's a centrarchid. And it's increasing in the Bay of Quinte. It was increasing in the Bay of Quinte, increasing in the Kawarthas, and increasing in the Mississippi River system. They're a really tasty fish. They should be fished really hard. Anyway, I want to look at the Mississippi River watershed, because what you may say is, well, you know, you've kind of cherry-picked some data that you have from eastern Lake Ontario. Are we seeing this, for example, in the Mississippi River system? So what we did was I wanted to look at the samples of fish that have been collected over the years in data for the Mississippi watershed, these river lakes, and I wanted to look at warm water and cool water fish recruitment in relation to water temperature. Unfortunately, we didn't have very much good water temperature data for the Mississippi River. So if you're into fisheries and if you really want to know what's going on, you need water temperature data. That's what you need. You can see there is an increase indicated by a shorter period of data set from Appleton, Carlton Place. And in fact, I looked at that in relation to the recruitment of two cold water species. One was lake whitefish, and the other was lake herring. And if you look at it, you can in fact see that there is a negative relationship between water temperature in those lakes and the recruitment of those species in those lakes. And if you look at the warm water fish, you can see a positive increase. It's just exactly what you would expect, given what we saw before. And there's a number of species and a number of lakes in this data set. The thing that's interesting is that over a 2-decade period in that Mississippi watershed, 60% there was a 60% increase in the recruitment of the warm water fish, and there was a 60% decrease in the recruitment of the cold water fish. And these were the lake whitefish and the lake herring. The thing that's interesting is there are lakes in that particular watershed where we know from ministry records, we have some samples from ministry records, that lake whitefish and lake herring existed, and they don't exist anymore. They've disappeared, and they were never fished, either commercially or by recreational fishers. So I think that's kind of interesting that this can happen and can go on. Now, if there's some fish there, and like I said, if they've invested in longevity, and they have, because some of those fish, those ancient fish we saw in those lakes were up to 30, 35 to 40 years of age. They would still be there, and they could recruit and give you now another year class, so they would still be there. Sorry about the table, but it's really the best example. It's a kind of an ancient one. It's the best example we have of walleye and river flows. And it comes from a study that was done on the Moon River in 1955 to 68. And there's a very, very nice study there that shows, in fact, that there is a correlation between year class strength of walleye and river discharge. And that's really important. In fact, it's my feeling that the largest year classes in many water bodies come from that particular relationship, not the shoreline spawners, but the river spawners. And that gives you the strong year classes. Well, I showed you a few minutes ago that, in fact, in the next 100 years, we're going to see a 33% decrease in discharge in the spring. So if you apply it into that relationship, which is a highly significant relationship actually, higher discharge, greater recruitment of walleye, then we'll see, in fact, in the next 100 years, a 24% decrease in the recruitment of walleye in the next 100 years. So that's not much, but that's going on in the presence of the fact that warm water species are increasing dramatically. And this species is not responding in a positive way, but it is being affected in a negative way. So now water level and droughting. Well, we got some interesting data from the St. Lawrence where we can actually look at long-term discharge of the St. Lawrence. And you can see that during that period, I hope you can see that that's from the 40s and 50s, here in the 60s. You can see major dynamics in discharge of the St. Lawrence. It wasn't stabilized at all. Moses Saunders was put in the late 50s. Didn't get the water stabilized, actually, until the 70s. So it was essentially still dynamic until about the 70s. The one point I want to make is look how low the water was in 64, 65. Dramatically low in 64, 65. And if you look at it in the 70s to the 2000s, you can see a major decline in water level, and that in fact is related to droughting. So there was droughting going on in the St. Lawrence over that time, although there is stabilization going on. Well, here's almost 50 years of pike recruitment in the St. Lawrence River. And if you look at pike recruitment in the St. Lawrence River, during that dynamic period, we had astronomically large year classes of pike being produced. Some years they were low, but the high water level gave us pike recruitment. They spawn in the shallows, in the wetlands, in the inundated wetlands in the spring. So I'm going to have three periods here. I'm going to have the dynamic period. I'm going to have a transitional period. Then we're going to have a stabilization and droughting period. And what the Q sum tells you is that really pike recruitment in the St. Lawrence started to decline rather dramatically during this stabilization and droughting period. Well, how dramatic was that? And how was it affected? Well, if you look at this relationship, this is the year class strength of pike, the number of young pike produced, and it's directly related to spring flooding and water levels. A higher water level gave us the strongest year classes of pike. Lower water levels gave us weak year classes of pike. So that's during the dynamic period. I selected that for 50 to 74. Now what's happened now for the stabilized and droughting period from 70 to 2000? No relationship whatsoever. So they're not responding because the water is not in fact inundating the wetlands enough to give us strong year classes of pike. Well, let's look at stock size. What's happened to stock size in the St. Lawrence? If you look at the bottom graph, starts here in fact in a standardized period of 1. If you look at the bottom graph, this is the actual population stock size of pike in the St. Lawrence River at the present time. Okay? And in this particular exercise, which we conducted for the International Joint Commission, looking at if given the amount of rainfall and the amount of discharge we could have had in the St. Lawrence River if it hadn't been stabilized, what would we have seen in terms of recruitment of pike? And basically, if you look at the blue, that is in fact the recruitment of pike we would have seen in the St. Lawrence River. So as a result of stabilizing and droughting, we now have a pike population that is modeled to be 70% lower than it would have been. So you can see that's a major change in terms of the available fish for consumption, for production, and for the enjoyable efforts that we all want to be involved in. I would suggest to you that as an angler, this is probably the most indicative way that you can see climate change. And that is, it's related to spawning behavior and hybridization. Start looking at your fish a lot more carefully, and because they give you indications of anomalous conditions. And anomalous conditions is related to spawning behavior. Now, spawning behavior could be that they spawn differently, they spawn deeper, or they spawn shallower, or they spawn later. And as a result, they may put them in another group of fish that they can hybridize with. The thing that's interesting, the first signals I ever got in this, I often ask anglers, do you see hybrids? What do you see? And the other piece of information I always ask is, what year was it? That's really important. Think about that. Keep notes. Keep mental notes. Anyway, hybridization is important. In fact, I noticed that remember I said 64, 65 was really low water levels in the St. Lawrence River. Well, lo and behold, this is northern pike. And in northern pike, muskellunge. Muskellunge and northern pike actually spawned together in 64, 65. And lo and behold, we saw hybrids come from that period. In 1982, this is I think a very poor amount, but it's a 1982 hybrid muskellunge, a pike cross, and we aged it accurately back to the 1965 year class. There's another number of other members of the pike family. There's one that I rather shudder to bring up with angling groups. It's called pickerel, right? When I fish walleye, I call them pickerel. When I do science, I call these small pike that are distinctly different pickerel. These are grass pickerel. This is a grass pickerel. It's found in eastern Ontario. It's found in various parts of southern Ontario. And it's in very shallow water, usually backwater areas, and it spawns very shallow. And this always used to be found in backwaters. And In fact, lo and behold, in recent years, we're now starting to see it come out. And it's now in the open St. Lawrence. It has a higher preferred temperature than northern pike, about 3 degrees higher. And so it's actually moving out. And lo and behold, in 1965, I was around then, I was looking for pike eggs, and I found pike and grass pickerel eggs together. They were found together in 65. And in fact, hybrids were produced during that low water year, when grass pickerel actually spawned with northern pike, as northern pike went out and spawned with muskellunge. And in fact, we're seeing more of these hybrids. In fact, in 1993, we saw a hybrid, this pike grass pickerel cross, and also in 2008. And just to prove that you can be observant and see these things, we received photographs, and I received information of a hybrid grass pickerel pike cross from Coles Creek, the Bone Shara River system, May 2012. I'm hearing more of this. I'm seeing more of this. And in fact, in the same year, I received a photograph of this particular fish, which was from the Constance Creek in the Ottawa River system, and it's a hybrid muskellunge pike cross. These hybrids now are much more prevalent related to this droughting. In fact, we're seeing other members of this family, which there's only one that really wasn't found in Ontario. It was the chain pickerel. It was found in New York State. We're seeing it moving north. It's invading north. And for the first time ever, we now have them documented from Lake Ontario. In fact, Jim Hoyle, one of the biologists at the Glora Fishery Station, did a nice job of documenting the fact that they were spreading north, this chain pickerel. This particular fish came from Parrots Bay in Lake Ontario. So they're spreading north. So we're going to see that kind of movement. So the thing is, what about growth? I talked about recruitment. What's happening to growth? Well, if we look at growth, I go in and I take the otoliths out of the fish, and in fact section them, get information from them, and I measure these growth increments and correlate them with years and correlate them with temperatures. And when I do that, if I look at smallmouth bass and I increase the water temperature 1, 2, and 3 degrees Celsius, you can see a substantial increase in the growth rate and length. 1 degree gives you 9.2% increase, and 2 degrees gives you an 18% increase, and 3 degrees gives you a 28% increase in growth rate. And you can see walleye can also benefit from warming in terms of growth rate, but not recruitment. And if you look at now a whitefish, you can see a decrease in growth rate. And it's exactly the opposite, of course, the warm years. So these effects are global. There's no doubt about that. They're major. And in fact, if we measure these increments, we see something interesting. I don't know if you can see 1992 on here, but you can see 1992, the Pinatuba event. The growth increment is very much narrower than it was for the year before and the year after. And actually, the La Niña event is very much smaller. So you see that. So you see in that walleye, you can see that cold event, in fact, decreased the growth of that walleye, is indicated by the otolith. So if you look at a whitefish otolith, you see exactly the opposite. See the whitefish, the growth increment in 1992. These, in fact, become benchmarks that we use to make sure our age assessments are, in fact, valid. Well, you can take this to the extreme. This is an otolith of a lake trout from the Arctic, actually. And it's right at the northern edge of its range. So what happened in 1992? Well, look how much slower the increment is in 92 compared to the growth increment before and after. So it would benefit from warming, as it would have a faster growth rate. The thing that is quite interesting is the Arctic is warming dramatically. And it's the Western Arctic that's warming. We've done lots of studies in the Arctic, and we've noticed that the Western Arctic is warming dramatically, where the Eastern Arctic is now warming, but it wasn't until very recently. So the Western Arctic is warming dramatically, and if you look at the number of frost-free days, for example, in Cambridge Bay, you can see a dramatic increase from the 50s to the present. In fact, there's a 26% increase in the number of frost-free days in the Western Arctic. And I would suggest to you that, in fact, that is affecting this polar jet stream. If the Western Arctic is warming dramatically, and we know it is, In my simple logic, why isn't that changing the way the jet stream is appearing and the way it's in fact changing in North America rather dramatically, giving us extremely cold falls and cold winters? Well, not so much cold falls, really cold winters. So I think that's something we should look into, but and maybe that's the explanation as to why we're seeing some anomalous conditions very recently. I'm sure it's related to the polar jet stream, and how that's affected by climate change, I can't really say. This, in my mind, is fishing adaptation at its very best. Here's a species increasing dramatically. Here's an angler that, in fact, is taking this fish, and in fact, in a winter fishery. So the new challenge will be to manage changing water resources and fish resources and fisheries in a changing and more variable climate. I think fortunately we can understand how we might see these changes occurring, and they are to some extent really predictable, but they're extremely variable. That's the problem. Changing environmental conditions necessitate more regular and rigorous monitoring. Now that's really important. And it's not only for fish and fisheries, but it's for the environmental conditions. We need to consider water body specifics. We need to have more and better science and data by location and by latitude. So we need to do more, really, to understand this and to take advantage of these resources. We need to publicize the fish are very sensitive indicators of climate change, and the fishes are responding and fish communities are changing, and that some fish are adapting, but displacement is more common. Unprecedented change is underway. We need to emphasize the increasing value of local fish resources and manage to take advantage of those that are increasing in abundance while protecting those that are declining and being displaced. Adaptation, we need to adapt by using local fish and fisheries. Responsible anglers are proven and important conservationists. Voluntary catch and release has contributed greatly to sustainable fish populations and fisheries. But I strongly believe that we should also enjoy eating our catch where and when appropriate. So the question is, how can we both adapt and mitigate? I would say that we should really reduce our carbon footprint by making local fish an important part of our diet. So I say let's go fishing. That's the best way to enjoy fresh local fish. Thank you.
So I know everyone's eager to get to lunch, so I'll wrap this up quickly. Although this isn't my first time seeing Dr. Casselman present on this topic, I still find myself walking away with a new appreciation for his passion and knowledge on the topic. I always learn something new and take away important messages, and there was many important messages in this presentation. So please join me again in thanking Dr. Casselman for his informative and forward-thinking presentation.
Thanks, Matt. Appreciate it. Oh, that's very nice. Thank you, Tony.